One of the strangest mysteries inherent to general relativity is the concept of a wormhole, a tunnel of sorts linking two separate points in space-time. Even stranger is the idea of a traversable wormhole, where one could travel instantaneously, or nearly so, to another part of the universe entirely, or possibly even another point in time. Whether wormholes can actually exist or would be stable is a hotly debated topic, creating one artificially even more so. But what if detecting one? Say nature allows them to exist on their own. Could we look for it? My guest today looked into just that and presents a way we might detect a traversable wormhole.
You have fallen into Event Horizon with John Michael Godier. In today's episode, John is joined by Dr. Dejan Stojkovic. Dr. Stojkovic is a research professor at the State University of New York at Buffalo. He's interested in answering fundamental questions on the interface between gravity, particle physics, and cosmology. His area of research includes the origin, evolution, and future of our universe, classical and quantum aspects of black holes, cosmological puzzles like dark energy and dark matter, beyond the standard model phenomenology, extra dimensions, evolving dimensions, and gravitational waves. Dr. Stojkovic co-authored a paper on observing a wormhole in October this year.
Welcome everyone to Event Horizon with me, John Michael Godier. If you enjoy what you hear, fall into the Event Horizon, hit the like button, and become an active subscriber by ringing the bell. Dr. Stojkovic, welcome to the program.
Thank you very much.
Now, Doctor, this idea of wormholes, this goes all the way back to a solution, it goes all the way back to Einstein and relativity. This idea that 2 points in space-time could be connected in some way. Now, it's always been a question as, could this really be? Do you think wormholes are a viable thing in the universe, or are they just something that's theoretical but may not actually be there?
That's an excellent question. I mean, we had a very similar situation with black holes themselves. Schwarzschild found a solution to Einstein's equations only 1 year after Einstein set up his equations of general relativity. But the solution was so unnatural. I mean, there was a horizon, there was a singularity at the center, that people refused to believe. I mean, not people, but scientists, prominent scientists at that time. They refused to believe that there is anything in nature that is described by this solution. So they thought it was just a pathological solution of Einstein's equations, and it has nothing to do with nature. It took them about 50 years. I mean, the term black holes was coined by John Wheeler in the 60s. So it took people about 50 years to accept that black holes actually describe something that can be found in nature. And then once they accepted that, and once we saw one black hole, then suddenly now we see many, many black holes around. I think, I'm not sure, you can never be 100% sure, but I can see a pretty good analogy with the wormhole solutions. So as you pointed out, wormholes are a legitimate solutions of Einstein's equations. And the first solution was actually found by Einstein. It's called Einstein-Rosen bridge. And it is a solution to the equations, valid solution, legitimate solution. And we do know that whatever is not explicitly forbidden by some principle, nature always finds a way to build it somewhere. So if you really want my opinion, I would say that's the situation. That it does sound pretty strange, pretty speculative, but if it is a legitimate solution of a legitimate theory, then most likely it is realized somewhere in nature.
Now, there's also the question of stability and traversability of a wormhole, that maybe if something tries to go through it, it collapses, as I recall. Now, what you're looking for is, you're saying, okay, well, what if they're traversable?
Right.
Then what would we look for to find one in nature? And your paper goes into looking at Sagittarius A, the supermassive black hole at the center of the galaxy. What connection is there between black holes and wormholes?
That first solution found by Einstein, actually that was a black hole connecting two different space-times. So, right, from a theoretical point of view, I mean, wormholes, they have to curve space-time itself pretty much. Black holes already curve the space-time pretty much. So it could be, right, the first place to look for wormholes is vicinity of black holes, because it could happen that a black hole harbors a wormhole. It doesn't have to be. There are wormhole solutions that have nothing to do with black holes. But the first hint, I mean, the first place to look for wormholes would be black holes.
Now, nearby Sagittarius A, there is a star. And the star's noteworthy because, as I recall, it's the fastest known orbit, or at least was up until recently, the fastest known orbit of a star. The star S2 plays into this. How do we use that star to detect a wormhole if it's present at this black hole?
So we follow the motion of this star for about 20 years, so we know its orbit pretty well. So if there is only central galactic black hole as a source of gravity, then the trajectory of that star should take certain shape, should have certain acceleration, certain properties. But if we have something on the other side, if that central object is not a black hole, but it's a wormhole, then there should be gravity leaking from the other side. So just like we have stars orbiting that central object in our universe, if that thing is a wormhole, there should be stars orbiting on the other side as well. Now, these stars, they also exert gravitational force. If wormhole is traversable, then gravity should leak through the wormhole into our space. Then we said, okay, if you have a typical perturbation, meaning like a typical star, just like S2 star, but on the other side. So a few solar masses star are rotating around the central object at a distance of a few gravitational radii. Then we said, okay, what would be the precision with which we know the acceleration of the star S2 so that we can see these small perturbations? We estimated that to be of about 10 to the minus 6 meters per second square. The current precision is 10 to the minus 4 meters per second square, so we're still not there. But I would say if you continue mapping the motion of S2 stars, so you continue monitoring the motion of this star, so either you take more data, so you take more years of observational data, or you use a better instrument, or you improve your statistical analysis. 10 to the minus 6 meters per second square is not too far out. I mean, it's from 10 to the minus 4 to 10 to the minus 6. I think it would take us about 1 or 2 decades at most. There is one actually important thing to say, which is connected with this. Right, if the central object is a black hole, then its gravity is static. But the star on the other side has most likely an elliptic orbit, just like S2 star has an elliptic orbit. So it should be possible to distinguish gravity, which is coming from such a time-dependent perturbation, so highly elongated elliptic orbit, from the gravitational influence of the central object, which is static.
Now, does it have to be another star? I mean, can it be like, say, on this side we have S2, but on the other side we have, say, a solar mass black hole or something like that? The principle is the same, right?
Yeah, principle is the same. So whatever is the source of gravity on the other side should be felt by star S2. That actually points out to a caveat. So if we detect deviations from the expected orbit of S2, so if we detect that anomalous acceleration, then we should look for more likely explanations. So maybe it's a black hole or a neutron star on our side that perturbs the motion of S2. So if you exclude that, then only then, if you exclude all of the more modest explanations that doesn't require the wormhole interpretation, so only if you exclude all of them and there is still anomalous acceleration, then you should start thinking about wormholes.
So that should create a lot of noise, though, because shouldn't there be a lot of those types of objects on this side interacting with us too that we can't see, like neutron stars and things like that? That should be a fairly densely packed area with stuff like that being around the supermassive black hole, right?
But just like you did with the star S2, I mean, you can map the motion of the stars and you can see what's the source of gravity. So then you model the orbits of those invisible orbits. That's how we discovered, actually, that's how we measured the mass of that central galactic black hole, by the motion of the visible objects around it. So if there are some invisible objects there, you can deduce their masses and their orbits by mapping the motion of the visible stars. So if you map all of the known perturbations, and there is still something left which you can't explain, there is still anomalous acceleration, even with the best modeling that you can do, then you should start thinking about more far out explanations, like a wormhole.
Now, wouldn't this say that it was found that there's a traversable wormhole there? Wouldn't that give us an insight into gravity itself? Because, you know, sometimes the quantum physicists are saying, well, maybe there's a particle involved. But if so, then that particle couldn't escape the black hole, right?
Right.
Therefore, Einstein's view of gravity would have to be valid, even on a quantum scale, I would assume.
But right, we have to distinguish two cases here. So one case, if the wormhole is traversable, then there's no problem of any particle and gravity going from one side to another. There is an issue there that our equations pointed out, but it has to be clarified. So we took a limit in which the wormhole mouth reaches the size of the event horizon. We still got the result that some gravity should leak. Even in that case, we were confused at the beginning. So that would mean that even non-traversable wormhole can leak gravity. So we try to understand the results. So we said, okay, gravity itself is just a property of the space-time itself. So if you perturb the horizon of a non-traversable wormhole, meaning that that thing has a black hole inside, meaning that you can send a particle through it, because particle will be trapped within the horizon. But gravity shouldn't be trapped, in a sense that if you have a source of gravitational perturbation on another side, then the horizon will be perturbed itself. And those perturbations of the horizon of the black hole should send information on another side of a black hole, or on another side of the wormhole. Just like you have a situation with the merger of two black holes, or a neutron star merging with a black hole. So it is true that no information can propagate from inside the horizon to outside. But if you smash two black holes, so at the beginning you had two horizons, but at the end they merge into one horizon. So obviously you can deform the horizon itself. And then the information about that deformation is usually sent out in terms of gravitational waves. So it's not impossible that you can deform the horizon of the black hole, and information about the deformation is propagating further away.
But only through gravity. No other electromagnetism, for example, can't.
No, yeah, that also follows from our equations. So when we try to do the same thing for a scalar field, we saw that in the limit when the wormhole mouth reaches the horizon itself, the scalar field stops leaking. It shuts off at that point. So only gravity can leak, no electromagnetism nor scalar field.
So this idea of a traversable wormhole in this form, would that be traversable only by gravity essentially, but if you took a starship out there, you couldn't go to another point in space-time by going through it, right?
If it is traversable, then yeah, potentially even starship can go through, or people, or objects, or other planets. But the mouth has to be big enough. To keep the mouth open, you need macroscopic amount of negative energy or anything else that will serve the same purpose, to provide some repulsive gravity, which is going to prevent the collapse of the mouth and keep it open. So the bigger the mouth it is, more negative energy and less plausible it is that you can form one like that.
And of course, with negative mass and that's highly theoretical, and we don't even know if it can even be made.
Right. We know that we can have fluctuations of negative energy density on microscopic scales, but we don't know how to do it on macroscopic scales.
So on microscopic scales, does that open the way for things like spooky action at a distance actually being a phenomenon of very tiny wormholes? I've heard that advanced. Do you think that that's one mechanism that could be?
Yeah, that's an interesting idea by Saskin and Maldacena. It's called like ER is equal to EPR, and it's practically a conjecture that whenever two particles are entangled, a wormhole is created between them. And that wormhole, it's essential that wormhole is non-traversable, because if it was traversable, then you should see particles appearing and disappearing all the time, which we don't. So these wormholes should be non-traversable. So for them, you don't need negative energy. But you are right that on microscopic scales, these quantum fluctuations can create small wormholes which are traversable. However, they are probably fluctuations. They are in some way fluctuations of the space-time itself. So they appear and disappear very quickly, probably at the Planck scale. And as such, they are very difficult to detect, probably impossible with current technologies. But it is possible. I mean, as an idea, it's quite possible that at those scales, these fluctuations of huge fluctuations of energy density at those scales can create all kinds of topologically non-trivial objects, including wormholes.
And we have to take a break. We'll be back in a moment where we'll talk more about how time plays into this wormhole equation.
Be sure to like, subscribe, and share the video. And now, back to John.
And we're back. Now, Doctor, the other big player here seems like it would be time, because some have advanced that wormholes could also be time machines and function as that. So is there some sort of protection here? Say you have gravity leaking through that prevents any sort of paradoxes within the 2 points in the universe that's being connected here.
So yes, you are right. So wormholes technically connect two different points in space-time. So that could mean two distant points in space, but it could mean two distant points in the space-time, meaning that if you jump into a wormhole on one end, when you exit on another end, you may end up at a different time altogether, which may create all of those paradoxes associated with time travel, like a grandfather paradox that I'm pretty sure everybody is aware of. I mean, what if you go backwards in time and you kill your own grandfather, then you don't exist, then who killed your grandfather, and so on and so on. So it could be that time travel is forbidden exactly because of that reason, that you create not self-consistent theory, non-self-consistent history of events. But it could be that, yeah, you can go through a wormhole and appear at a different time, but just you can't alter the history, or you alter it some different way. I mean, you split. I mean, all kinds of explanations are now possible that the universe splits in two, and then you change the history, but that's not the history within your own universe. The different version of your life actually happens in some different universe. But these are highly speculative solutions, so I wouldn't go in that direction. I would just say that technically you can end up, when you go through a wormhole, you can end up at a different point in time, but as long as you are not changing the causal history, then you are fine. That's good. That's allowed. There's nothing to forbid it.
Is it possible that it only goes in one direction, like the arrow of time, and that if you go through one, you only end up in the future? Is that a viable possibility, or does there have to be past time travel at all involved?
So that you end up and that you can that the arrow of time goes right, but right. So that's a very interesting point. So that would mean that there is a global arrow of time in a so-called multiverse. So even in two completely disconnected spaces, there is an arrow of time, and arrow of time is usually associated with entropy. So the point that you are making is pretty interesting. So that would mean that due to the communication through the wormhole, one or many wormholes which are connecting these two disconnected universes, it could happen that they share degrees of freedom, so they probably share entropy. Therefore, there is a unique arrow of time. Therefore, that arrow of time should be respected even when you jump into a wormhole and appear there. Yeah, that's quite a plausible possibility that I didn't think of before, but thank you very much for pointing that out.
Now, another question I would ask too is, does it have to link 2 points in space-time? Can a wormhole link 2 separate universes?
That's what I meant. That's what I meant. Actually, when you look at the solution itself, at Einstein-Rosen bridge, that first solution, you can literally see that these are 2 infinite universes connected through the hypersurface of the black hole horizon. So there is a black hole that connects 2 infinite universes. So these are different universes altogether.
Now, you say infinite universes. In other words, they're infinite, which brings up a lot of interesting possibilities in itself. Why do they have to be infinite?
They don't have, but that's the solution. It's asymptotically flat universe in which your coordinates take all of the possible values. I mean, from minus to plus infinity. So it is infinite. You can make it more complicated. Instead of asymptotically flat universe, you work with de Sitter or anti-de Sitter. Actually, one of our previous papers, we found a solution similar to Einstein-Rosen bridge, but it's just in a de Sitter space. And we used the properties of the de Sitter space. First of all, it's finite. There is a finite horizon. A second, de Sitter space has a positive cosmological constant, and we do know that positive cosmological constant acts as a repulsive gravity. So we use that fact to stabilize 2 black holes and a wormhole between them. Because if you put 2 black holes and connect them with a wormhole, there will be attractive gravity. The configuration is not stable. It will collapse on its own. But if you do it in de Sitter space, that repulsive gravity of the positive cosmological constant can keep these 2 black holes apart at a stable configuration, and then you find a legitimate stable solution in de Sitter space. So it doesn't have to be, the universe doesn't have to be infinite. It could be finite.
Now, really quickly, de Sitter space, that's sort of a construct to express space, correct? Could you give a little bit of detail as to what that is and how physicists use it?
Actually, we do live in a de Sitter space. So you do know that we detected dark energy, that the universe is expanding with acceleration. You can't get acceleration if you just have ordinary matter in it, because ordinary matter and energy will have attractive gravity. So any initial expansion should be slowing down because gravity is always attractive. But if you put the whole construct in a de Sitter space, meaning if you put cosmological constant in it, that cosmological constant will have repulsive gravity. So now you can have accelerated expansion of the universe, as if gravity was repulsive. So if the universe is dominated by dark energy or a cosmological constant, like in de Sitter space, then you naturally get accelerated expansion of the universe. So, and we do actually, it looks like we do live in a de Sitter space.
Yeah, that's the whole underpinning of dark energy, is the universe does appear to be speeding up as far as expansion goes. And that's observational.
Yeah, exactly.
Now, back to the wormhole. Now, this should be, it's convenient to look at the supermassive black hole at the center of the Milky Way, but could this happen at other black holes? Or is there like a mass limit on what could happen here? In other words, do you really need a supermassive black hole for it to also function as a wormhole, or can this be all black holes?
No, right. The method works for any binary system. So binary system of 2 black holes, or a black hole, or a star. So whatever system has one of its members as a potential wormhole, and you follow the motion of its companion, I mean, you can apply absolutely the same mechanism there. There's no limit. There's no limit.
So in other words, if we are ever in somewhere in the future, far future, we're traveling space and we come across a black hole, it might be possible for us, if it's traversable, to go through it and actually make use of this at some point. Again, in very speculative far future, of course. But it would be possible then at pretty much any black hole.
Right. As I mentioned at the beginning, yeah, we studied a wormhole which is in the background of Schwarzschild metric, meaning in the background of a black hole. But it's not necessary to have a wormhole which is such a solution. So you can have wormholes, so you can have objects connecting two distant universes or two distant points in space-time that have nothing to do with black holes. They can be just some peculiar configurations, and there are no black holes in the vicinity. So it doesn't have to be, but most likely place to look for wormholes are the places where space-time is already curved in a violent way, and these are black holes.
Now, what about, so say black holes, which you have massive disruptions of space-time. What about smaller, less massive objects like a neutron star? Could a neutron star have a wormhole around it? Would that be more likely as well?
Theoretically, yeah. So probably, it might be a little bit technical to explain what we did. So the solution that we were dealing with takes two black hole solutions, but we cut them a little bit at the point which is larger than the horizon, and then we paste them together. In that sense, that object that harbors a wormhole doesn't have to be a literally black hole. It could be a neutron star, because the point where we paste two spaces together is not a horizon, is larger than a horizon. And neutron stars are very compact objects which are larger than a horizon. So yeah, technically you can have a wormhole which is harbored by a geometry of a neutron star rather than a black hole, because both of these geometries are Schwarzschild geometries. The only thing is that black hole goes all the way to the extreme, so there is an event horizon and there is a singularity at the center. But any massive star curves the space-time, and it's described by a Schwarzschild solution outside of the surface of the star.
Now, monitoring S2's motion to see if there's indeed a wormhole here. Monitoring that, is there any instrumentation coming online in the near future that's going to help you constrain this down?
Yeah, a very large telescope in Chile or Keck Observatory in Hawaii. Both of them are very powerful. So if you keep monitoring S2 with these instruments, then you should nail it down. I'm pretty confident that we will reach the needed precision pretty soon. As I said, at most 1 decade or maybe 2, but it's just like 2 orders of magnitude. I think that's doable.
And also, data is being collected already on this star.
Yeah, the data that we already have a precision of 10 to the minus 4 meters per second squared for the acceleration. We need 10 to the minus 6. So maybe, theoretically, yeah, if you improve your statistical analysis, then it could be that you can do it even with the current data. But I would say we need more data.
All right, Doctor, it's been a really interesting chat, and I appreciate you appearing. I hope you'll come back and visit us sometime here on Event Horizon.
Yeah, it was my pleasure.
And we'll talk more about your other work next time, perhaps.
Yeah, no problem. Thank you very much for your invitation.
So, say they exist, natural traversable wormholes. Would you step through, not knowing where you might end up or when you might end up? The idea that the universe could be crisscrossed with natural shortcuts is an alluring one, allowing for faster-than-light travel in a manner still consistent with general relativity, but comes with the possibility of paradoxes. Paradoxes aren't good, and may preclude such a thing from ever existing, but at least now we have one way to look for them. Wait, what?
John, a meteorite just hit the car.
What? Oh no! The LeBaron! My baby! The body's ruined, it demolished the trunk. This is going to cost a fortune to repair.
It's been hit by a meteorite. That finally makes it worth something.
It was already priceless, to me anyway. Well, at least it scared the possum out of the LeBaron. On that note, join us next week for a discussion about detecting life on Mars and how we may have already done it. See you then.